We know that once you have certain charges, charges can be plus q and minus q, can be positive or negative. And once you have a charge, it can be either a point charge, which is a point is actually zero dimensions. Yeah, point is zero dimensions. 1D, then you have a line charge. Yeah, it can be a line like that, or it can be a 2D, what we call as maybe on a surface like a carpet. And 3D is really a volume. Yeah, so this charge can be distributed in any manner. So this kind of 0D charges is what we call as point charge. We call it as point charge. That if there is a point charge of, let's say, plus charge here, then the electric fields are going to be always coming out. And what do we mean by electric field? Is a force experienced by a unit positive charge. So if I have a +1 charge here, for sure this plus charge is going to repel it, so it's going to be coming out. So it's going to be coming out like this. Yeah, at any point it's going to be radially outside. Yeah, whereas if I had a negative point charge, if I had a negative point charge, then the electric fields are going to be pointing inside, because that's how, if I bring in, imagine you're bringing in 1 plus Coulomb charge and placing it at this point, it's going to get attracted. It's going to be attracted by this negative charge, so it's going to be going in all the time, right? So you see that there is going to be an influx in this case in negative charge, and if it's a positive charge, it's going to be an outflux. Yeah, so this is something the physics tells us. Yeah, this is how it is going to behave. But then how do you write this mathematically? Turns out that if I were to have two charges, if I were to have two charges, or even in this case, if I were to have any location R, if I want to find the electric field at any location R, that location R could be this point in space. It's a position vector on that point in space. That electric field due to this plus Q is going to be Q over 4 pi epsilon naught. Q over 4 pi epsilon naught. That means if higher the Q, higher the electric field. But electric field is a vector, right? We are missing that electric field quantity there, which is 1 over the distance between these 2 points. And if this is my R vector, let's say this is my origin, this is my R vector, and this is my, let's call this RQ vector. Then you have the R minus RQ vector, which is this guy. R minus RQ vector is going to be this guy. And you know the electric field is going to be acting in this direction, yeah, because any plus charge here is going to be repelled out radially outside. So this becomes R minus RQ, the whole squared. I haven't written the square yet. And it's going to be in the direction of R minus RQ vector. So I need to find a unit vector in this direction. So I would divide that by its magnitude. So there's already a square there. So square plus 1 is going to be cube. So this guy is the electric field due to a unit positive charge, which is plus q. If it were be minus q, then you're going to simply replace the q by minus q. All that it's going to change is the direction. For example, if this charge becomes a minus q charge, then in this direction, this vector is going to go opposite in direction. The magnitude will still be the same. All that has changed is the direction. The plus has become the minus. Okay, now that's just a point charge, but in reality, none of it is a discrete point like that. Everything is continuous. Space is continuous. That means you're having these charges distributed. Yeah, they are distributed maybe most of the time uniformly. Yeah, when you're saying the surface charge, for example, it's uniformly distributed, then the charges are all equally distributed across the entire surface. Yeah, so similarly you can have that, we call it as rho L, then you have rho S, then you have rho V. Rho L being the Coulomb per meter, rho S being Coulomb per meter square, and rho V being Coulomb per meter cube. So then how do we go about doing it for distributions? For example, if you have a parallel, if you have a plate like this, instead of finding the complete electric field due to the entire plate, you break it down into a smaller problem. You find a small little charge first, which you call it as dq. Then you find what is the electric field due to this dq. Certainly that is going to be acting in this direction at this point R. So we went ahead and did how to find the electric field due to that. So if the integral is given, you end up getting the electric field to be two values. And if you notice that, why is that so? Two values. One is when h is less than 0, and the other one is when h is greater than 0. So let's take h greater than 0. It's very obvious that if there is a point here, if I have all the plus charges uniformly distributed on this disk, certainly if I bring in a unit positive charge, it's going to be going shooting up to the sky, right? It's going to be repelled out. So the direction of the electric field is going to be this way. So it's going to be plus z hat. I'm missing a z hat here. So it's going to be in the plus z hat direction for this guy. So it's a plus z hat for h greater than 0. But when it's h less than 0, for example, if I'm underneath the plate is positively charged, I'm going to have all the charges being pushed downwards. So that becomes a negative z hat direction. It has to be in the negative z hat direction. So you get these two expressions here, where it is going to be dependent on the radius of the disk.